All right, this section is going to be on Faraday's law. Now, the last section we didn't cover last time was on magnetic flux, okay? So I'm going to start by discussing magnetic flux, and then we'll discuss Faraday's law, okay? So let me define magnetic flux. This is just like electric flux, except that we have magnetic field in this case. So this is a measure of the amount of magnetic field that crosses a loop perpendicularly, okay? So this is a measure of the amount of magnetic field, amount of magnetic field that crosses a loop perpendicularly. Crosses a loop. We're talking about conducting loop perpendicularly. Okay. So let's say you have this loop over here, and you've got magnetic field crossing it like this. Okay. So we can decompose this into horizontal and vertical components, right? Now the horizontal, the component parallel to the plane of the loop doesn't contribute anything to the flux. It's only the perpendicular component that contributes to flux, okay? So you take the component of this one, B perpendicular, okay? And let's say the area of this loop is A, then the magnetic flux is defined to be the perpendicular component of the magnetic field times area, okay? Now, if you remember, the direction of the area of the loop is perpendicularly out from the loop, right? So the direction of the area is also this way. So if the angle between the area, this is A, and the field is theta, then we can say B perpendicular equals B times cosine of theta, okay? So the magnetic flux would be the strength of the field times the area of the loop times the cosine of the angle between the area and the field, okay? So theta is angle between area. This is angle between area and field, okay? So this is assuming the magnetic field is constant throughout the loop, but most of the time it's not going to be constant, so let's generalize it. So if you've got a situation where the magnetic field varies or the area changes and stuff like that. So what you do is you take a small element of the area, okay? On that area, you can assume the magnetic field to be constant, right? And the angle should be constant. So you take d phi b, okay? And so you've got the magnetic field on that small part over here times dA, and then the angle between dA and the field, okay? If you remember, this is just b dot dA, right? So this is the flux in a small region over here. And then to get the total flux, you just integrate, okay? So this is the flux crossing the loop, all right? So this is a general formula for the flux. Now you remember, we did this also for electric field, but in the case of electric field, we're looking about, if you remember Gauss law, we're talking about surface integrals on a closed surface, okay? This is area enclosed by a conducting loop. That's what we're looking at in this section. So this is the formula for magnetic flux, the general formula for magnetic flux. So if you want, you can say if B is a constant, you can get this formula. Now let's simplify this because most of the time you might deal with the case where B is a constant. So if B is a constant, and then you can take out B, right? So you've got B, that's the integral of dA, okay? And this would be the area of the loop, okay? So if the magnetic field is constant, you can just use the following formula, B dot A, which is also B times A times the cosine of theta, okay? So the general formula would be the integral, but if you know the magnetic field is a constant and the angle between the area and the field is also constant, then you can simplify it with this formula, okay? If the magnetic field is a constant. Now, look, the flux could be positive or negative. If the angle is acute, cosine is positive, so the field is going to be positive if the angle is acute. But If the angle is obtuse, this would be negative. So the flux would be negative. Actually, if the angle is 90 degrees, the flux would be 0, which means there is no component of the magnetic field that crosses the loop perpendicularly. Okay, so this is the general formula of flux. Now let's look at some examples. Example. Now suppose, let's say we have this loop. Let's say it's 2 meters by 2 meters. Okay, it's a conducting loop over here. And let's say the magnetic field goes like this. Let's say this is B equals 10 Tesla. Now, can you tell me what the flux crossing this loop is? Okay, well, let's write it. The area is the square. The area is going to be 4 meters squared, right? 2 times 2. And the magnetic field we're given is 10 Tesla. What do you think is the angle between the area and the field? What's the direction of the area? Remember, the direction of the area is always perpendicularly out, right? The direction of area is always perpendicularly out. So if the area is perpendicularly out and the field is parallel to the plane, what do you think is the angle between the field and the area?
90 degrees.
Oh, 90 degrees. So our theta is 90 degrees. So you see, in this case, the flux is B times A times the cosine of theta. So you've got, it's going to be 0. So B is 10. This is 4, and then you've got cosine of 90, we get 0. In other words, this field does not have a component that crosses this loop perpendicularly. Okay? All right, let's say this is A. And let's say we have this rectangle, maybe 1 by 4, okay? And the magnetic field is perpendicularly out, like this, perpendicularly out, okay? And let's say the strength of the field is maybe 5 Tesla, okay? So let's calculate the flux. Well, we have the area is a rectangle, 4 times 1. We have 4 meters squared, right? And then we have the field, which is 5 Tesla. What is the angle in this case between the area and the field?
Are we saying that the area is perpendicularly out as well?
Always. Area is always perpendicularly out.
I just want to make sure it's out and not in. So it'd be 0 degrees?
Yeah, 0. The area is always perpendicularly out. It's always a dot, okay? So the field is a dot, so they're parallel. So theta equals 0, okay? So theta equals 0. So we have flux equals B times A times cosine of theta, okay? So this is going to be 5 times the area, which is 4, and then we got cosine of 0, which is 1. So you get 20 Tesla meter squared, okay? Now suppose, how about it goes like this? Let's say this is maybe 2, the radius, okay? And then now the field is perpendicular in like this, okay? So let's say the field is 2 Tesla, okay? So we have B equals 2 Tesla. The area is, this is a circle, so it's going to be pi times 2 squared, that's 4 pi, okay? What is the angle in this case?
180.
180, very good. You see, area is always perpendicularly out, like this, and the field is perpendicular in, so they're opposite, so the angle is 180 degrees, okay? So in this case, we have flux equals BA cosine of theta, so it's going to be, the magnetic field is 2, we've got 4 pi over here, we've got cosine of 180, cosine of 180 is -1, so you get -8 pi Tesla meter squared, okay? So you see flux could be positive or negative. If the perpendicular component is the direction of the area, you get positive flux. If it is opposite the direction of the area, you get negative flux, okay? So that's how we calculate flux. We've done this for electric flux, but the same thing, except that we have magnetic field in this case, all right? Now, if you remember, when we first discussed magnetic field, we said that magnetic field forms complete field lines, right? They form complete loops. So let me say that again. Magnetic field lines form complete loops. Complete loops. Okay? So magnetic field lines, we don't have magnetic charge. That's the reason. You remember for electric field, the magnetic field lines, they start from positive and they end up in negative like this. Okay, they go like this. These are electric field lines, but we don't have magnetic charge. So magnetic field lines form complete loops. Okay, they form complete loops. For example, if you take a permanent magnet like this, the lines will eventually form a complete loop. You might get a big circle, but eventually it's going to be a complete loop like this. Okay, because we don't have magnetic charges. So magnetic field lines form complete loops. Okay. So what do you think would be the magnetic flux evaluated over a closed loop? Let's look at, surface, magnetic flux over a closed surface, So let's say you have this closed surface over here, such as a sphere, okay? Now we want to calculate the magnetic flux over the entire surface over here. So that means you take a small area element and you take a dot product with the field and then integrate it with the entire surface area. But remember, magnetic field lines form complete loops, okay? So they might be like this. What does that mean? You see, you have magnetic field entering and magnetic field leaving. You have both kinds of flux. If the field forms complete loops, then some of them are going to get in, some of them are going to get out. That means some of the flux will be positive, some of the flux will be negative. Actually, if you add up all of them, you get zero, okay? So magnetic flux over a closed surface is zero because there is no origin for the field. It's a closed loop, okay? So that's actually called Gauss law for magnetic field. So let's take Gauss law for magnetic field. Gauss law for magnetic field states that magnetic flux over a closed surface is zero. And the reason is because magnetic field lines form complete loops. So mathematically, you can relax this. You see, this is magnetic flux over a closed surface. Let's put over here, closed surface over here. Closed surface equals zero. Okay. Do you remember what the magnetic flux for electric field was over a closed surface? Gauss law for electric field. For electric field, that was proportional to the charge enclosed inside the surface. You remember that? But for magnetic field, the surface integral over the closed surface is zero. And the reason is we don't have magnetic charges, magnetic field lines form complete loops. So if you take any surface, some of the lines will go in, some of the lines will go out. So they cancel each other and eventually get zero. Okay. Now, there are four very important equations that we call Maxwell equations in electricity and magnetism. All this was discovered experimentally by people like Coulomb, Ampere, Bartsauer, and so on. It was Maxwell who organized all these experimental findings mathematically. And so he came up with four equations, okay? So far we have discussed three of them. One is Gauss law, that the flux over a closed surface of electric field is proportional to the charge, okay? This is the second one. The flux of the magnetic field over a closed surface is zero. The third one is what we discussed last week. Do you remember? If you take the line integral of the magnetic field over a closed path, what do you get? That's mu naught current plus epsilon d phi by dt. Do you remember that? That is Ampere's law. So we have discussed three of them. The fourth one is Faraday's law, and we're going to discuss that one today. Okay, so let's look at Faraday's law now. Faraday's law. This law says that whenever the magnetic flux crossing a loop changes, there will be an induced voltage which is equal to the negative rate of change of flux. Let me say this one. Whenever the magnetic flux crossing a loop changes, there will be an induced voltage. There will be an induced voltage equal to the negative rate of change of flux. Negative rate of change of flux. Change of flux. Okay, so let's write this mathematically. This is the induced voltage. Let's say this is the induced voltage over here. It is a negative of the derivative of magnetic flux with respect to time. Okay, so this is the mathematical statement of Faraday's law. Okay, now as you know, magnetic flux depends on three factors. Okay, if the magnetic field is a constant, you remember we have this formula, B times A times the cosine of theta, right? So there are three ways by which you can change the flux. You can change it by changing the field. You can change it by changing the area. You can change it by changing the angle, okay? So there are three different ways by which you can change the magnetic flux and produce an induced voltage. So what does the induced voltage do? Well, the induced voltage will produce current, okay? So you've got a loop over here, and somehow you're able to change the flux. Then the
Oh, I got stuck on the hole.
Excuse me? You have a question? No? Okay. So let's say you have this loop over here. If somehow you're able to change the flux crossing this loop, then there will be an induced current, okay? So in other words, you're changing mechanical energy to electrical energy. That's how they produce the voltage or the electricity that we use. All right? So, and then let me tell you the meaning of this sign over here. Now, if the induced voltage is positive, that means the current is flowing counterclockwise, okay? If the induced voltage is negative, that means the induced current is flowing clockwise, okay? Let me write the same convention over here. E induced greater than 0 implies induced current is flowing counterclockwise. Induced current counterclockwise, okay? That's the meaning of the sign of the voltage. And induced voltage less than 0 implies induced current is clockwise. Induced current is clockwise, okay? Now, let's get a formula for average induced voltage. Probably most of the time we're going to deal with averages, okay? So let me simplify this for an average. So let's look average induced voltage, average induced voltage, okay? How do you obtain average in calculus, remember? Well, if you've got this over here, what you do is first you find the area over here and you divide by the base to get the average. In other words, you get the rectangle of equal area and that becomes the average, okay? So the average induced voltage like this, what we can do is, if you want to find the average over time interval delta t, well, we can integrate the function negative d phi b by dt over time, okay? And then we can go from t to t plus delta t, and then we divide by the base, or delta t, okay? This is the definition of average. So dt cancels out. This is basically the integral of d phi b, basically the flux, okay? So from this you get, this is 1 over delta t, okay? And the integral of this would be phi at t plus delta t minus the flux at t, okay? But we can just say delta phi or phi flux minus phi initial, okay? So this is basically negative change in flux divided by delta t, which means the negative of the final flux minus the initial flux divided by delta t, okay? So that's what how you calculate the average induced voltage over a given time interval, okay? Maybe let me put it in a box over here. So if you're asking for average, right, induced average, it is negative delta phi b by delta t, okay? And if you've got something changing instantaneously, if you're looking for the instantaneous voltage, then you have to do the derivative, okay? So let's look at some examples. As you said before, there are three ways of changing the flux: by changing the field, by changing the area, and by changing the angle. Now, if you remember in the experiment we did, what did we change in the experiment we did when we did Faraday's law? Do you remember? You see, we didn't change the area of the coil. The coil was fixed. What we changed was the magnetic field. When you drop the magnet through the coil, As it gets nearer, the field increases, okay, and as it goes away, the field decreases. So what we changed it in the experiment we did was magnetic field, okay? So let me consider an example of producing voltage by changing magnetic field, okay? So let's say we have the square over here, okay? Maybe it's 2 meters by 2 meters. And let's say I have this field over here, perpendicularly out. The direction is fixed. So let's say initially the field was 5 Tesla, okay? Now suppose the field is increased to 10 Tesla, let's say in 0.5 seconds. The question is, calculate the average induced voltage. Calculate the average induced voltage. The average induced voltage. Okay, so in this case, we're not changing the area, we're not changing the angle, we're just changing the field. Okay, the area is fixed, so we've got initial area equals final area equals 2 times 2, which is 4 meters squared. Okay, so this is the fixed area, it's not changing. How about the angle? What's the value of the angle in this case? The field is perpendicularly out. What's the direction of the area? Always perpendicularly out, right? So they're both parallel, so the angle is 0, all right? So you've got initially the angle was 0 and we didn't change it, so that also equals 0, okay? Maybe we'll call this one just A, and we call this one just theta, okay? But the magnetic field is changing. The initial was 5 Tesla, now we're changing it to how much? 10 Tesla, and the time interval for this change was 0.5 seconds, okay? So let's look at the formula for the induced voltage. This is negative delta phi by delta t, okay? That's negative of final flux minus initial flux divided by delta t, okay? So the area and the angle are constant, so we can factor them out. So this is I induced average equals negative. The area is constant, the angle is constant, so we just have B final minus B initial over here divided by delta T, okay? So this is the average induced voltage where this is constant, that's why I factored out, okay? So it's for the numbers. So the area was 4, the angle was 0, right? And the final flux was, the final flux was 5, this is 5, and then divide by 0.5. Okay, so cosine of 0 is 1, so you've got negative 4 times 1, and this is 5. So you get negative 20, right? Negative 20 divided by 0.5, you get negative 40 volts. So this is the average induced voltage during this time interval. Okay, now what does the negative mean? This sign over here? What does the negative mean? The negative means if there's induced voltage, there's an induced current, and that induced current is flowing clockwise. Okay, because the induced voltage is negative, that tells me the induced current is flowing clockwise. Okay, so this is an example of producing voltage by changing the magnetic field. Okay, let's look at another example, an example of producing voltage by changing area. Okay, so let's look at another example. Suppose we have the following. Once again, let's say we have this square over here. Okay, maybe it's 2 by 2 again. But now we have perpendicularly into the paper field. Okay, and let's say the field is maybe 10 Tesla. Okay, but now suppose the shape is changed to a circle. This is suppose the shape of the wire is changed to a circle, let's say in 0.2 seconds. Okay, now you see the field is not changing, the angle is not changing. What's changing is the area. The area of the student is not going to be the same. Okay, so what we have is we're not changing the field, so you've got BI equals B final equals B equals 10 Tesla. What's the angle in this case? Can you tell me? What's the angle between the field and the area? Remember, the area is always perpendicularly out, right? So the angle between perpendicularly out and perpendicularly in is?
180.
180, very good. So we have theta initial equals theta final equals theta equals 180 degree. What is changing is the area. The initial area is the area of the square, okay? So we have A initial is 2 times 2, that is 4 meters squared, okay? How do you think we should calculate the area of this circle? Can you propose? How do we know what the radius of the circle is? Now remember, the area will change, but it's the same wire. So the length of the wire will not change, okay? We're talking about the same wire. So the perimeter of this square and the perimeter of the circle should be the same, okay? That's how we determine what the radius of the circle is, okay? So let's say you have this circle over here, this dimensions are x, and you change it to a circle whose radius is r. The perimeter of the circle, which is 4x, okay, should be equal to the perimeter of, the perimeter of the square, which is 4x, should be equal to the perimeter of the circle, which is 2 pi r, okay? So the radius of this circle should be 4x over 2 pi, or 2x over pi, okay? So in this case, our x is 2, x equals 2. So the radius is 2 times 2 divided by pi, or 4 pi, okay? So now we know the radius of this circle over here. We can calculate the area. So the final area is pi times the radius of the circle squared, which is pi. I'm sorry, about pi. So this is pi times 4 over pi squared, and we get 16 over pi, okay? So this is my final area, the area of the circle, whatever this. This is my final area over here, meter squared, okay? Now we can do the indecent voltage, average indecent voltage, all right? So this is our formula. Indecent voltage equals negative delta phi by delta t, or you can say negative final flux minus initial flux divided by delta t, okay? Also, we're told delta t is 0.2 seconds, all right? Now, in this case, only the area is changing, the field and the angle are not changing, so you can factor that out. So it equals negative b times the cosine of the angle, that's going to be factored out. And then we have final area minus initial area divided by delta t, okay? Okay, so we'll just put in the numbers now. Negative b, our magnetic field is 10 Tesla, right? Negative 10, our angle is 180 degree over here, like this. And then the final area is 16 over pi. The initial area is 4, okay? Divided by the time, 0.2, all right? So this number is bigger than this one. This 4 is 16 over by 4. So this number is going to be positive, and positive times negative is going to be negative. So the indecent voltage, well, there's another negative over here, I'm sorry. So we've got this is positive, we've got negative. The indecent voltage is positive in this case, okay, when you calculate it. So the indecent voltage in this case, indecent voltage average is greater than 0. What does that mean? What does the fact that the voltage is positive means? It means
The current is counterclockwise.
very good. So the current in this loop, this changes area, is going this way in a counterclockwise direction. Now, if you know the resistance, you can actually calculate the average current, okay? Let's say if the resistance of the loop, let me say it implies counterclockwise over here, counterclockwise current. All right, if let's say the resistance of the loop, let's say is R, then the current, the indecent voltage is simply going to be the indecent voltage divided by the resistance, okay? So if you know the resistance of the coil, you can actually calculate the average current in the coil, okay? Now, let's look how we can change the voltage by changing the angle, okay? So let's look at another example. All right. So let's say I have this rectangle over here. Let's say maybe this is 4, this is 2. Okay. Maybe we have this magnetic field over here. Maybe let's go this way. Suppose this is a magnetic field going this way. Let's say it's B is 10 Tesla. Okay. Now, suppose the loop is rotated by 90 degrees. The loop is rotated by 90 degrees in, let's say, maybe 0.5 seconds. Okay, so this loop is rotated by 90 degrees. So let's say eventually it gets over here like this, where this angle is 90 degrees. Okay, all right. So in this case, we're not changing the shape of this one over here. So the initial area, the final area are the same, and that's the triangle. It's going to be 4 times 2. So the equals area equals 4. Okay, the area is fixed. How about the magnetic field was not changing, right? So you can say B initial equals B final equals B equals 10 Tesla. What is changing over here is the angle because we're rotating it. Okay, so what do you think is the initial angle? You see, initially the plane of the loop was parallel to the field. Remember, the area is perpendicularly out, right? So what's the angle? What's the initial angle?
0 or 90.
90 degrees. Okay, so we have theta initial is 90 degrees. Okay, now how about when you rotate it perpendicularly? What do you think is the final angle? So
0.
0. You see, it was like this. This is the area. When you rotate like this, it becomes parallel to the field. You see it? You have this before, and then you rotate by 90 degrees. The area becomes parallel to the field. So the final angle is 90, I mean, 0 degree, okay? So now we can do the calculation, and delta T we're told is 0.5 seconds, okay? So the average induced voltage is negative final flux minus initial flux divided by delta T. In this case, the field and the area are constant. We can factor them out. And then you've got cosine of theta final minus cosine of theta initial divided by delta T. Okay, so this is our formula. So the magnetic field is 10 Tesla. Let's see, 10 Tesla. So we've got negative 10. The area is 4, right? 4. And then we have cosine theta final. Theta final is 0. So you've got cosine of 0 minus cosine of pi over 2 divided by 0.5. Okay, so what's cosine of 0? We have negative 40. Cosine of 0 is 1. Cosine of 90 is 0, right? Divide by 0.5. And that gives me negative 80 volts. Okay, so this is the average voltage induced during this process, and it's negative. That means the induced current is flowing counterclockwise. Now, producing voltage by changing angle is the most common way, okay? So let's look at how they do it in a generator. You see, all the voltage that is produced by rotating a coil. So let's look at an example. Let's look at a generator, how a generator works. A generator is a device that converts mechanical energy to electrical energy. This device converts mechanical energy to electrical energy. Mechanical energy to electrical energy. Okay, let's see how it does it. So simply what they have is, they have a magnet like this. Okay, so let's say the magnetic field goes this way, all right? And then they have a coil over here. They have a coil over here. Let's say the direction of the area of this coil is this way, let's say, okay? Perpendicular to the coil, all right? So this is the area vector, this is the field vector. Okay, now suppose you rotate this coil. Okay, this angle will keep changing, right? Let's say it's rotating with angular velocity omega. So if it is rotating with angular velocity omega, if it is rotating with, let's say, angular velocity omega, then the angle equals, can you tell me? The angle equals angular displacement, angular frequency times time, okay? So it's rotating with angular speed omega, then the angle is omega times time. All right, okay? Now suppose the area of this coil is A, and let's say N is number of turns. Okay, so in this case, you see the flux is changing constantly. So we're looking at instantaneous voltage in this case. So we're going to the derivative. So first, let's obtain the flux. Okay, so the flux in this case is B times A times cosine of my theta is now omega t. This is my flux. Okay, this is flux per turn. But I have n turns. Okay, so total flux would be n times of this one, n times BA times cosine of omega t, okay? If you've got n turns, all these turns are being crossed by this magnetic field, so you get multiplied by n, okay? Now let's do the voltage, okay? Did I state the B? Okay, this is B, okay, this is A, and we got theta, so we got everything, all right. So let's do the induced voltage. Now we're looking at instantaneous voltage over here. Okay, that's negative, the derivative of flux with respect to time. Okay, so number of turns, the magnetic field, and the area are constant, and then you've got the derivative of cosine of omega t. Okay, what's this derivative? The derivative of cosine is negative sign, right? So that makes one positive. And then from chain rule, we can get angular velocity out. So this is nBA times angular speed, and then sine omega t. Okay, so this is the induced voltage. All right, so you can rotate this. Let's say if you rotate this by falling water, that's what hydroelectric power is. You can rotate by any means, but the end result is you're converting the mechanical energy to electrical energy. Okay, when rotated, that's mechanical energy, and that mechanical energy is converted to electrical energy according to this form. If you look at the voltage that comes out from the wall outlets in our houses, if you connect a computer, you'll see it actually varies like a cosine, like this AC voltage. We're going to do an experiment on AC next week. The voltage looks like this one. The reason is that's the way it's produced, by rotating a coil inside a field. Okay, so this is the amplitude. So you can say this is E max. E max would be NBAW. Okay, so the amount of voltage you get from this depends on the angular frequency. It depends on how big the coil is, how big the field is, and then how many number of turns you have. And of course, the period would be 2 pi over omega, right? The period would be 2 pi over omega. So that's how they produce the voltage that we use. All right? Okay. So these are the 3 ways by which you can produce voltage and convert mechanical energy into electrical energy. Okay. Now we're going to look at what they call motional EMF. Let's look at motional EMF. In this case, what they do is you have a U-shaped conductor like this, okay? Place a magnetic field. Let's say the magnetic field is a dot over here like this, and let's say its magnitude is B, okay? Now what they do is they put a rod over here, a conducting rod, okay? And then they move it, okay? Look over here now. You've got a closed circuit over here, right? When you move the rod, what is changing? Is it field, is it area, or is it angle? When you move the rod, you see this is a loop. So when you move the rod, you're changing the area. So this is a way of producing voltage by changing the area, okay? Let's say this one is moving with speed v in this direction. So we want to get an expression for the induced voltage you get by moving this rod with a speed v in a U-shaped conductor. Okay, suppose let's say the position of this one changes. Well, let's write the flux of this one first. So let's say the length of the rod is L. Okay, so what's the area? Let's say this is X over here. The area is L times X, right? So the area is L times X. All right. Now we're interested in the sign, so I'm just going to put it in absolute value. Okay, emotional. I'm going to absolute value over here. Well, first let's do. Let me use the flux and then let's do the derivative. Okay, the flux is, the angle is 0 in this case. See that? But as I've said, we're interested in sign. But the area is perpendicularly out. The field is perpendicularly out, so the angle is 0. So it's basically B times L times X. That's the flux, okay? This is the area, and the angle is 0, which is cosine of 0, which is 1, okay? Now let's do the motional MF, which is a derivative of the flux. If you're interested in sign, it's the derivative of the flux, okay? So it's just the derivative of this one. The derivative of B times L times X, okay? So the magnetic field and the length of the rod are constants. We can take it out. So you've got, this is B times L times the derivative of X with respect to time. What do you think this represents? What's the derivative of position with respect to time? What do you think?
Velocity.
Velocity, right? But dx by dt is v, which is velocity. Okay, so we have the following formula. The amount of voltage you get from emotional MF, that's by moving a rod in a magnetic field, is equal to this one. Magnetic field times length times speed, okay? So this is the formula for the amount of voltage that you get by moving a rod, an U-shaped conductor, in a case where the magnetic field is perpendicular to the plane of the U-shaped conductor. All right? All right. Now we want to look at the dynamics of this rod. Okay, suppose starts with initial speed v naught. You give it initial speed v naught, and then what happens? Let's look at the dynamics of the rod. Dynamics of the rod, which means we're going to look at Newton's second law. Okay, so let's say suppose the rod starts with initial speed v naught. With initial, so you give it initial speed v naught and let it go. What do you think is going to happen? Well, look, you have a rod over here. If it is moving, there's going to be change of flux. If there's change of flux, there's going to be induced voltage. That induced voltage produces current over here, right? What happens to a current carrying rod placed in the magnetic field? You remember? There is magnetic force. There is magnetic force on a current carrying rod. So this will be acted upon by a magnetic force, okay? And that magnetic force is going to oppose the speed, otherwise it's going to accelerate it, which is against the rule of nature, okay? So as this external force pushes this way, the magnetic field will oppose it, okay? So let's look at the force. The force acting on the rod, okay? So let's say the rod is going this way, and the magnetic force is going to oppose it. We're going to see later, then this rule says the direction of the induced current in saturated is opposite, because the direction of the current will be in saturated as the motion of this is opposite. Okay, we're going to do that. We're going to do that later when we look at Lenz's law. So the force is, let's say, at least absolute value is current times length times b times the sine of the angle, right? But they're perpendicular in this case. The field and the current, they're perpendicular. The current's going this way. The field this way. They're perpendicular, so you can say times sine of 90. Okay, so this one is just ILB. Okay, but we know the current. What's the current? The current is the induced voltage divided by the resistance, right? Our resistance. That's what the current is. So we can say that this force over here is equal to the induced voltage. We just obtain expression for over here. That's the motional EMF, BLV. So this one's going to be, this is induced voltage. I'm talking about the current right now. So the current is BLV, which is the induced voltage, divided by the resistance, right? This is the induced EMF. If the resistance of the coil is R, then that's the current you get, all right? So let's look at the force. The force is this current over here, BL speed, divided by R, and then times L, times magnetic field. I'm just substituting over here, okay? So what do you get? You've got B squared, L squared over resistance times speed, okay? So this is the force acting on the rod. But remember, this force is going to oppose the speed, okay? Now let's apply Newton's second law. Newton's second law, we're going to find the dynamics, how the velocity changes with time or the position changes with time, all right? Newton's second law says mass times acceleration equals force, right? Or mass times the derivative of the velocity with respect to time equals force. Equals force. But what this force is going to oppose the speed, so we have to put a negative, okay? So this is going to be negative B squared L squared over R times speed. So that's our equation, okay? The mass of the rod times acceleration equals the negative. The reason for negative is the magnetic force is going to oppose the speed, the direction of the speed, okay? So let's solve this equation, all right? We're trying to find the velocity as a function of time. So let me write again, dv by dt equals negative b squared L squared, negative b squared L squared over R times speed, okay? So we have solved this differential equation, all right? Now, whenever possible, first, you should try separating the variables when you solve differential equations, okay? So let me first divide by m over here, okay? And then I'm going to put the speed over here. So you've got dv by v equals negative b squared L squared over mass times resistance, and then you've got dt over here, okay? Now we're going to integrate. Remember the initial speed is v naught at equals 0. At equals 0, the speed is v naught, okay? And we're trying to get the velocity as a function of time for arbitrary time over here. That's our equation, okay? So what does this integral gives me?
Natural log.
Very good. This is ln v equals negative b squared L squared over mr. Well, integrated, we're going to get t, okay? T, or from 0 to t, that'll give you this one, okay? And then what's the speed? Well, let's do this first from v naught to v. It's going to be ln v over v naught, right? We've got negative b squared L squared over mrt. And then we change it to an exponential. We get b over v naught equals e to the power of negative b squared L squared over mrt, okay? So the speed as a function of time, you see, is the initial speed times this one, L squared divided mrt. So what does it mean? This one is a decreasing function, right? This one goes to 0. So if you plot the graph, it is the velocity which start from v naught over here. You see, this one will go to 0 as t goes to infinity because it's negative sign, right? So what's going to happen is the speed will decrease and eventually goes to 0 exponentially, okay? And now let's get a formula for the position as a function of time, okay? Position as a function of time. Position with time. Okay, we know that the velocity is a derivative of position with respect to time. Okay, so instead of v, I'm going to put dx by dt, and then I get the following: dx by dt equals negative v naught e negative b squared L squared over mrt. Okay, so dx equals this one, negative v naught e negative b squared L squared t over mr dt. Okay, so we're going integrate over here. Okay, let's say it starts from the origin from 0. Let's say the initial position 0. Or if you want, just you can say delta x if you want. This goes from xi to x final. So this will be delta x. Okay. So what's this integral over here? Okay. So it's going to be inverted, right? It's going to be negative mr over b squared L squared, and then e negative b squared L squared over mr. Okay. And this is from 0 to t, right? Okay, so we have, this is negative, the initial speed. Well, let's put them together over here. So this is positive over here, v naught mr over b squared L squared. And then at t, this would be e negative, what is it? That's b squared over here. Negative b squared L squared over mr t minus 1, right? If you put there's t over here, if you put 0, just get 1. All right. So the delta x, is there a negative over here? Let me see. No, there's no negative over here. I'm sorry. This negative, no, there is, this is positive over here. There is no negative over here. There's no negative over here. All right, it's positive. So, again, well, now there's negative, we have a negative over here. Okay, so we can write like this. This is b naught mr over b squared L squared, and then we can just flip this one, minus e negative b squared L squared over mr t. Okay, so that's how the position of the rod will change as a function of time. Okay, so what happens at t equals 0? Well, start from 0, right? It's going from 0. But then what happens? You see this term over here goes to 0, right? And so this will be the maximum value of the displacement. Okay, so if you plot the graph over here like this, as t approaches infinity, this goes to 0. So you're left with this one, right? So the limit as t approaches infinity is going to be over here, which is b naught mr divided by b squared L squared. Okay, and at t equals 0, this becomes 1. We put 0 over here, so you get 0 over here. So you start from 0. So, and this is the limit. Okay, so the displacement will approach this asymptotically. Okay, but will never get beyond this distance. All right, it approaches this distance very slowly eventually. All right, so this is the dynamics of the rod. If you start with the speed v naught and let it go, that's how it will move to a certain limiting value exponentially. All right. Okay. Now we're going to look at ways of writing Faraday's equation in terms of an integral. Okay. Remember, Gauss law we wrote in the form of an integral. And the Gauss form magnetic field, we wrote in the form of an integral. Also, Ampere's law, we wrote in the form of an integral. So we're going to write Faraday's law in terms of an integral. Okay. You remember what the definition of EMF is? Does anyone remember? Let's say Faraday's law in the form of an integral. In the form of an integral. The reason this voltage is EMF is because EMF is the potential difference you get by converting non-electrical energy to electrical energy. Okay, so in this case, we're converting mechanical energy to electrical energy. That's why it's EMF. Okay, if you remember, the definition of EMF was work done per a unit charge. Okay, so the definition of EMF is work done by the source, whatever is changing to electrical energy per unit charge. Okay, now we're going to define electric field corresponding to the work done by the source. Okay, so I wish I could say ES, but I'll just keep it as E. Okay, let E be the electric field due to the source. Okay, this is different from the kind of electric field you get by separating charges. That's electrostatic field. But in this case, we're talking about field corresponding to the force exerted by the external force converting the mechanical energy into electrical energy. For example, in the case of battery, it will be the chemical force. Okay. In the case of a generator, it would be the mechanical force rotating the coil. Okay. So this is different from the kind of electric field we talked before. That corresponds to electrostatic force, but this one is a different kind of electric field. Okay. So what is work? You remember, work is F dot ds. All right, this is the definition of work. But if you define this electric field, I can write this force over here as Q times this new kind of electric field. Electric field is the source, okay? So this work, let's say the source, would be Q, the integral of E dot ds. Okay, this would be my work. So what's the EMF now? If you evaluate this on a closed loop, you see, we get this is work by the source per unit charge, and this Q, the integral of E dot ds. Now we're talking about a loop, so we're going to do this in a complete loop divided by Q. Okay, so this induced voltage actually equals the integral of this electric field dot ds. Okay. Now, if this was electrostatic electric field, what do you think this integral would be? Remember, the work done by a conserved force is independent of the path followed. Okay, so if you do this integral for an electrical force on a closed path, your initial point and final point of zero are the same, so it's going to be zero. Okay, for electrostatic force, this will be zero because electrostatic force is conservative. But we're not talking about electrostatic force over here. We just represented the external force in terms of electric field. That's all we did, but this is not the electrostatic field we did before. Okay, so now we can write Faraday's law in this way. Faraday's law now can be written as follows. This induced EMF, which is, let's evaluate in a counterclockwise direction of E dot ds, equals the negative derivative of magnetic flux with respect to time. Okay, so this is another way of writing Faraday's law. You take any closed path, okay, and you do this integral, will be equal to the negative rate of change of the magnetic flux. Okay, this is the integral form of Faraday's law. If you do this over any closed path, that equals to the negative derivative of the magnetic flux with respect to time. That's the magnetic flux crossing that closed loop. Okay, now let's demonstrate this by means of an example. All right, so let's look at an example. Suppose I have the following solenoid, like this. Okay, and then we have, let's say we have this one over here. So we have current over here, okay? Let's say we have current I over here. This is counterclockwise like this, okay? Now, to make the calculation easier, I'm going to select my path for doing this integral to be a concentric circle, okay? So we're going to do this integral on a concentric circle like this, okay? So that we can take advantage of symmetry, okay? Now from symmetry, we can make the following conclusions. From symmetry, first, we can conclude that, but why are we going to have electric field over here? In this case, we're going to have current that varies with time as a function of time, right? So the magnetic field will be as a function of time, all right? So this would be non-zero because the magnetic field is changing with time, all right? That's why we expect electric over here. If the magnetic field or this flux is changing with time, then that will result to an electric field throughout space, okay? So that's the expression we're trying to get. All right. So from symmetry, first we can say that the electric field is constant on this circular paths because they're all subject to the same conditions. Okay. So we can say that, let's say this distance over here is R perpendicular. Okay, R perpendicular. So the first is the electric field. The electric field is constant on a concentric circle, on a concentric circle. Okay, so that's one of our conclusions. And the other thing we can go from symmetry is that the electric field is tangential to the concentric circle. Okay, the electric field is tangential to a concentric circle. Tangential to a concentric circle. What does that mean? At any point over here, for example, is going to be either this way or this way. Okay, it's going to be tangent. It's going to be tangent to this circle. Okay, so with these two symmetry calculations, we can do this integral very easily. Okay, so first let's do E dot ds. E dot ds. Okay, ds is tangent to the circle. Okay, and so the electric field is tangent to the circle, so ds and the electric field, they're either parallel or anti-parallel. Okay, so let's say the component be denoted by ES. It could be plus E or negative E depending on whether the current is clockwise or counterclockwise. So this will just be the component times ds. Okay, if it is 0, we have positive over here. If it's 180, will be negative. So this is a component. All right, so this is the value of E dot ds. Okay, so now let's do the integral over a closed path. E dot ds equals the integral of ES ds. Okay, but we said from symmetry ES is constant, right? So we can take it out of the integral. It's a constant. So this equals ES, the integral of ds. What do you think is the integral of ds? You divide this in small ds's, okay, and then add them up together. What do you get?
The circumference.
Circumference, very good. So the radius are perpendicular. So this one is 2 pi r perpendicular. 2 pi r perpendicular. Okay. So this integral is simply 2 pi r perpendicular times the electric field. Okay. Now let's work on the other side. The other side is negative the derivative of magnetic flux with respect to time. Okay. So what's the magnetic flux? Well, the magnetic field is inside is almost constant, okay? And over here, they're approximately perpendicular to each other. So the magnetic flux is B times A, okay? So the magnetic flux is the magnetic field times A, okay? And there are N terms. This will be in N times BA, all right? N is number of terms. So the flux is, this is flux per one term, B times area. The area is this one we're talking about. The magnetic field is crossing this area, okay? Even though we're talking about this over here, there is no magnetic field over here. The magnetic field outside is approximately 0. So we have magnetic field only over here. So this is the area we're talking over here. So if the radius over here is R, our area is pi r squared, okay? This is pi r squared. So you can say this equals N B pi r squared. That's our flux. But what is the magnetic field solenoid? Do you remember? What's the formula for the magnetic field solenoid? Do you remember this formula? B equals mu naught number of turns per length times current. Okay. So in this case, this is a function of time over here. All right. Let me put the L over here as a solenoid. So this is our length over here. L over here. Okay. So if you remember, the magnetic field, the solenoid is this one over here. So we're just going to put over here. Instead of B, we're going to put this over here. So you've got N pi r squared. This is N pi r squared. And then we have this for the current. Mu naught N over L times the current. with respect to time. Actually, this is the flux. Okay, this is the flux. All right, n pi r squared mu naught n divided by L. So we have n squared. This is mu naught pi r squared, and then we've got n squared over L, and then times the current. Okay, so this is our flux. Now we can apply Faraday's law. This is Faraday's law. Faraday's law is the integral of E dot ds is negative the derivative of the flux with respect to time, right? But we already obtained this expression over here, remember? So over here, this integral over here is 2 pi r perpendicular times the electric field, okay? So this is 2 pi r perpendicular times the electric field, and then negative the derivative of this expression over here, mu naught pi r squared over L n squared current. So only the current is a function of time in this case. So we have the following: negative mu naught n squared pi r squared over L, the derivative of the current with respect to time. Okay, and then we just divide by 2 pi r perpendicular. We have a formula for the electric field. So the electric field is the negative mu naught n squared pi r squared, and then we're going to have 2 pi r perpendicular times the length over here, and then times the derivative of the current. Okay, so this is an expression for the electric field. So what that tells is a magnetic field changing with time gives rise to electric field. All right, so if somehow you're able to change the current in solenoid, you actually create magnetic field throughout space according to this equation, which varies inversely proportional with the distance from the solenoid. Okay, so this is the integral form of Faraday's law. Okay, we're gonna summarize Maxwell's equations later, but for now, let's look at what they call Lenz's law. All right, Lenz's law. Lenz's law has to do with a negative in Faraday's law. Okay, remember this is our equation: I induced equals negative d phi b by dt. Okay, so Lenz's rule helps you to determine whether the direction of the induced current is clockwise or counterclockwise. Okay, now you get it quantitatively if you know the numbers. You see, if the flux is increasing, then the induced voltage is negative. It tells you the current is going to be clockwise, right? If the flux is decreasing, you got a negative over here, the induced voltage becomes positive, you get a counterclockwise current. Okay, so if the flux is increasing, the current will be clockwise. If the flux is decreasing, you'll get a counterclockwise current. But this rule helps you to do it qualitatively. Okay, so let's state it. This says the direction of the induced current, the direction of the induced current, is in such a way, as to oppose the codes, Okay, so this rule helps you to determine the direction of the induced current qualitatively. Okay, so we're just going to demonstrate by using some examples. All right, so let's start with the following example. Suppose, let's say, we have the following U-shaped conductor. Okay, U-shaped conductor. We've seen how to produce voltage using this one. Okay, suppose, let's say, the magnetic field is perpendicularly out like this. Okay, like this, perpendicularly out. Now, suppose the rod is moving to the right. How is it moved? Well, you should apply an external force to move it. Okay, so what's the cause for the change of flux as producing the current? What's going to happen is, as you pull this one, you're changing this area, and the change in area will cause induced voltage, and that induced voltage will produce current, right? So what's the cause? This says the direction of the induced current is such as to oppose the cause. What's the cause for this flux? It is external force that's pulling to the right. That's the cause, okay? So first you have to identify the cause before you can use this rule. So let's say the cause. The cause is external force pulling to the right. The cause is external force pulling to the right. Pulling to the right. All right? Okay. So this rod, now it has an induced current in it, and it's placed in the magnetic field. And if you remember, a current carrying wire placed in the magnetic field is acted upon by a magnetic force. You remember that? If you've got a current carrying wire placed in the magnetic field, it's going to be acted by a magnetic force. The question is, which way should the magnetic force be? Should it be to the right? Should it help with the external force, or should it oppose it? According to this rule, it should oppose this force. Okay? So we conclude the direction of the magnetic force should be this way. Okay? So the magnetic force should be to the right. So the conclusion is magnetic, to the left. Magnetic force should be to the left. Should be to the left, to oppose the cause, to the left. And the reason is to oppose the cause. You know, if that wasn't the case, you can create a perpetual motion motion. If it helps external force, that means you can create a perpetual motion motion, but that's not how nature works. It opposes the cause. If you do something, we're going to try to stop it, okay? All right. Now, how do we find the direction of the induced current? We know two things. We know the direction of the force. We know the direction of the field. Now I have to find the direction of the current. You remember? They're related like this. If this is current, can you see it, man? Okay, you remember? Index finger was current. This one is field. This is magnetic force. Okay, so we're saying magnetic force is to the left, this way. Okay, well, the magnetic force is this way. Okay, but the field, I don't like this one. Can you see it? So the force is to the left. Okay, this, my middle finger, which is the magnetic field, is perpendicularly out. So that tells you my index finger is pointing down, okay? So the idea is, you know now two directions. You know the direction of the force, you know the direction of the field. Using the right-hand rule or the screw rule, you can figure out the direction of the current, okay? So the current is going this way, okay? So you have force going this way. The magnetic field is going up. Let's see. Yeah, I don't know if you can see it. This is the force. This is middle finger magnetic field, and then the current goes down. Okay, so that way you can determine the direction of the current. Okay, so in other words, the direction of the current is clockwise over here. Okay. Now let's see how you can do it mathematically. You've got the field, you got the area, and the area and the field are parallel, so it's positive, right? And then as they increase, the flux is increasing, right? So that means your derivative is positive, but you have a negative that gives you clockwise current, okay? You can do that way, but this is another way of doing it. Okay, so this implies current, induced current is counterclockwise. Induced current, I mean clockwise. Induced current is clockwise. You can say from the right-hand rule or the screw rule. From right-hand rule. Right-hand rule. Okay, let's look at another example. Another example. Suppose I have a permanent magnet. Let's say this is a permanent magnet over here. Let's say this is my north pole, this is the south pole. If you remember, magnetic field lines, they come out of the north pole, they go into the south pole. You remember that? Magnetic field lines, they go like this. This is the magnetic field. but they go into the South Pole, they come out of the South Pole. Okay? Now, suppose I have this loop over here. This loop over here. Okay? Now, suppose the loop is pulled away from the magnet, away from the magnet. Away from the magnet. Okay? Why do you think the flux would change if I take it away? If I remove the loop away from the magnet, what do you think is changing? What happens if you go farther away from the magnet?
The
The strength of the field decreases, right? So as you go away, what's happening is the field is decreasing. Okay? It's that change of the magnetic field that will produce a change in flux in this loop, and that change in flux will give an induced voltage. Okay? So the cause for this change of flux over here is a decrease in magnetic field. By pulling it away, we're decreasing the magnetic field. So let's identify the cause. Cause is decrease in magnetic field. Decrease in magnetic field. Okay? Okay, now what's going to happen? Okay, we pull away, the magnetic field changes, that changes the flux. The change in flux produces induced voltage, and the induced voltage produces induced current. Okay, so there is induced current over here because of the change in flux. Okay, and that induced current in this loop is going to produce its own magnetic field, like a solenoid. This is a solenoid carrying current produces field, right? So that induced current over here is going to produce magnetic field. So the question is, should that magnetic field be this way or this way? We're talking about induced field over here. The field is the induced current over here. And Lenz's law tells us the direction of the induced current should be in such a way as to oppose the cause. So if the cause is decrease, what should be the effect of this magnetic field? It should be to increase it. Okay, so the conclusion is the direction of the induced current in such a way as to increase the field. Okay, so this implies direction of induced current should be in such a way as to increase the field. To increase the field. Okay, now we have two fields in play. We have the field due to the magnet, it's called B, and then we got the field due to this induced current over here. Okay, so the net field is the field, this is a permanent magnet, plus the induced field. So if this is to increase, do you think the induced field should be parallel or opposite to the external field? Does it increase it when it is in the same direction or is it opposite direction? To increase it, it has to be parallel to it. Okay? If it is parallel to it, this is plus. If it is opposite to it, this is minus. Okay? So we conclude that the induced magnetic field should be parallel to external field if it is to increase it. Okay? So this implies the induced field should be parallel to the external field or to the magnetic field. Should be parallel to the magnet field to increase it. Because the causes decrease, it has to increase it. Okay? So that means this is to the right. So the induced field has to be also to the right to increase it. Okay? So that tells you it has to be to the right. It has to be to the right. to the right. Now, you remember in the case of a solenoid, this is a one coil solenoid over here, the direction of the current and the direction of the field are related by the right hand rule. You remember that? Like this. If this is current, this is field, right? So now we know the field is to the right, right? So the current is counterclockwise, okay? You see that? So the field is to the right, so the current is counterclockwise, okay? We have already said the field is to the right to increase this field. If the field is to the right from the right-hand rule, then the direction of the induced current should be clockwise, okay? So this implies from the right-hand rule, for a solenoid, the direction of the induced current should be counterclockwise. Current should be counterclockwise. All right, let me summarize. Now we have this loop, we're pulling it to the right, okay? When pulled to the right, the strength of the field is decreasing. So what's causing the change in flux crossing this loop over here is a decrease in magnetic field. That's our cause, okay? So the change in flux will produce induced voltage and induced current in this loop over here. According to Lenz's rule, the direction of that induced current should be in such a way as to oppose the cause, okay? So if the cause is decrease in magnetic field, that induced current should flow in such a way as to increase the magnetic field, okay? But this one is to the right. If it's to increase it, then this one has to be to the right. It has to be in the same direction. And then once we figure out the field is to the right in this, we just have to use the right-hand rule to figure out the direction of the induced current. Okay? All right. So that's pretty much about Faraday's law, but now we finished all Maxwell's equations by now. So I'm going to summarize Maxwell's equations. Okay, so let's look at Maxwell's equations. Maxwell's equations. Now, as I've said, all this electrical stuff was people like Faraday, Ampere, and so on. They discovered this laws experimentally, okay? But it was Maxwell. He studied all the experimental findings and was able to organize them into 4 equations. These 4 equations are to electricity and magnetism, as Newton's 3 laws are to mechanics. These are the cornerstone of electricity and magnetism. You can express anything in electricity and magnetism using these 4 equations. It was a very big accomplishment. It took him 10 years to do it. It was really an amazing work that he did. Okay, so we're going to summarize. The first one we did, if you remember, is Gauss' law for electric field. This is Gauss' law for electric field. What does that say? Can you tell me? The surface integral of the electric field on a closed surface is proportional to
the charges contained within.
Very good. So this law says the surface integral of the electric field on a closed surface is proportional to the charge, to the total charge enclosed inside the surface. This is one of Maxwell's equations. And if you remember, mathematically, we can write like this. This is closed surface over here. Closed surface. If you take this integral over here of a closed surface. Our constant was 1 over epsilon. So you've got Q enclosed over here divided by 1 epsilon or 4 pi k. Okay. So this is the first of Maxwell's equations. Okay. The second one, actually we did it today, is Gauss law for magnetic field. The second one is Gauss law for magnetic field. Do you remember what this law says? It has to do with the surface integral of the magnetic field over a closed surface. What do we say it's equal to? The surface integral of the magnetic field over a closed surface is 0. The reason is magnetic field lines do not have a source to be enclosed inside. They form complete loops. Okay, so this law says the surface integral of the magnetic field over a closed surface is 0. Okay, so let's write it. The surface integral of the magnetic field over a closed surface is 0. Okay, so let's write this in mathematical form. So if you do this in a closed surface, B dot dA, the surface integral of the magnetic field is 0. Okay, so it's the second of Maxwell's equation. That's the basic difference between electric field and magnetic field. Magnetic field does not have a source like a charge. Okay, all right. The third one is Ampere's law, but as we've seen before, it has been modified by Maxwell, so it's called Ampere-Maxwell's law. Okay, so this law is called Ampere-Maxwell law. Okay, and what does that law say? It has to do with magnetic field. This is line integral. Okay, if you take the line integral of the magnetic field in a closed path, it's proportional to the total current crossing the closed path. Okay, so let's write it. The line integral. Now line integrals over paths, surface integrals over surface. Okay, so the line integral of the magnetic field over a closed path is proportional to the total current crossing the path, perpendicularly crossing the path. Okay, but remember there are two kinds of currents. You remember that? So this one says if you do this over a closed path in a counterclockwise direction, this one over here, B dot ds, that is proportional, or mu naught times, you've got the normal flow of charges, is represented by current, and then Maxwell has to include a new kind of current called the displacement current to make the two consistent. Okay, and that is, if you remember, it is epsilon times the derivative of the electric flux with respect to time. Okay, so this is Ampere's law. Okay, this was discovered by Ampere experimentally, and this was introduced by Maxwell theoretically. Well, what he was trying to do is very easy. Let's say you have a capacitor like this over here. Okay, let's say you connect this to a resistor. Now you have current over here, but you see, you remember Kirchhoff's laws? What comes in should be equal to what comes out, right? You remember Kirchhoff's rules? So in a capacitor, you have something comes out, but we don't have what comes in. That's at least what people thought before. But Maxwell, he said there should be another kind of current over here, and that is displacement current. And now you can look at it very easily. What happens if you've got a dielectric over here? What happens is the molecule would be pulled between positive and negative ends. Okay, so depending on the strength of the electric field, this positive and negative ends, they come closer and further, right? If the electric field is big, the molecule becomes polarized further. If the electric field decreases, the molecule gets shorter, right? So that is motion of charges. That's what we mean by displacement charges. You see, these charges of the molecule are moving depending on the strength of the electric field. That's what we call the displacement charges. So outside, we have the real current, which is this one over here, flow of electrons. And inside, we have the movement of the positive and negative end of the molecules that we call displacement current, okay? So this is what we call Ampere's law. So this is the third of Maxwell's equations. And then the fourth one is what we learned today, Faraday's law, okay? So let's take Faraday's law, number 4. Faraday's law. This says the line integral of the electric field on any closed path is proportional to the negative rate of change of magnetic flux. So this is the line integral of the electric field. Remember, this electric field is the source. It's not electrostatic electric field. Of the electric field on a closed path. On a closed path is proportional to the negative rate of change of magnetic flux of magnetic. Do you have a question? Do you have a question?
How lucky we are to get the wins we got.
All right. Okay. So let me write it. And this is, you take the line integral on a closed path of the electric field. Is this one over here. And the constant proportionate is 1. You get the negative of the derivative of the magnetic field in respect to time. Okay. So a changing magnetic flux gives rise to electric field. Okay. And a changing electric field, this one over here, gives rise to magnetic field. Okay. So when electric field is changing, magnetic field is created. When magnetic field changes, electric field is created. Okay. So these are the integral forms of Maxwell's equations. Okay. At this level, they're written as integral forms, but if you happen to take a higher level physics course, these are actually written in the form of differential equations. Right? But at this level, they're written in the form of integral form. Okay. So these are the basic equations of electricity and magnetism. These are to the study of electromagnetism, as Newton's 3 laws are to the study of mechanics. All right. So that's it for today. Do you have any questions? No? Okay, so remember, we're taking a test on Tuesday, but this chapter is not included. Okay? All right, I'll see you tomorrow. Bye-bye.
Thank you, Professor.
You're welcome. Bye-bye.